Welcome to Out of the Blank.
Welcome to another episode of Out of the Blank podcast. I'm here with Andreea. It's nice to have you on the show. Please, for everyone out there listening, do you want to introduce yourself?
Hi, Robbie. Thank you for having me. So I'm Andreea Font. I'm an astrophysicist at Liverpool John Moores University. I study the formation and evolution of galaxies using computer simulations. So what it means is that we're trying to model the formation like a galaxy like Milky Way, for example, using just computer code. And the overarching goal of my research, I would say, is to understand how our own galaxy has formed in a universe, which apparently we don't actually know.
Can I just ask how you wanted to research something? Because I mean, space is so vast, and it seems like whenever I talk to someone who's involved in space, if it's not actual science-based stuff, it's more about the idea of alien life. Now, I like the more science aspect to it, like how this universe came to be, because the idea that God created the universe and it goes into this, I'm like, that's cool and all if you want to believe that, but I kind of want to put more scientific into it, and I want to understand is that how is each planet in this solar system, or all these different combinations of events that happen from stars to whatever you want to say, they're so uniquely different. And it seems like if you're in the same space, like you can see that with people, you have a group of people in the same space, they tend to evolve with their environment. They tend to evolve in kind of the same way, like humans. We all have two arms, we all have two legs. That's not like that with planets. Planets have, I mean, maybe the same shape in some aspects, but the sizes are completely different. The atmospheres are completely different. The whole construct of the whole entire planet, if it can sustain life or not, is fascinating to me. And I think it's very, very easy to not overthink into those aspects of what this planet is or what this solar system is. But I mean, okay, here's another example. It's a funnier one. So yeah, if you're studying the Milky Way, if you're looking at the Milky Way, people would go, "Oh, look how beautiful it is! Look how awesome it is." That's true. But then there's my thought, which goes, "Did you know we're going 250,000 miles an hour towards the Andromeda galaxy, and in 4 billion years we're going to collide?" Now, that's just like a random off thought, but that should make you so interested into the topic.
Yeah. No, I think you hit it right on. I think this is also my motivation of what I'm doing. I'm trying to understand how galaxies form. And I think you can do it different ways. Computers help you kind of put a lot of data in, because there's a lot of data to model, as you say, planets and stars and dark matter and everything. So you kind of put it all into a computer and you just follow a set of physical laws, basically gravity, which tells how planets to move, how stars to move, how dark matter moves, and so on. And then a bit of gas physics. So we also have gas and stars. And I think we're getting there. You ask about planets. I think we're getting there as well to model planets. At this moment in time, the computer simulations are not powerful enough to go the full kitchen sink model, as they call it, have everything in it, including the planets. But I think in a few years, we're going to get to it. So yeah, the other thing you said about the fascination with the Milky Way. Yeah, I grew up in a very busy city where I couldn't actually see the sky because of the buildings. So I think I discovered Milky Way later on in life, and it really hit me when I actually learned about the Milky Way, that there is a Milky Way there. And by the way, our ancestors actually were able to see the Milky Way without any light pollution and so on. And yeah, nowadays, if you actually go to a telescope, you actually see this band of light across the sky, which is actually fascinating. And I think we're missing a lot, but by not actually being able to see with our own eyes. So with the computer simulations, we actually recreate the formation of a galaxy inside a computer. And the end goal is try to get a realistic galaxy that kind of looks like the Milky Way. And yes, as you said, that there's planets are like people. And also stars are like people. They have different ages and they different shapes and they have different evolutionary histories. And all of this goes into a computer simulation. So we do take into account when we study, for example, stellar populations, as we call them, different stars. We take into account that they would have a different evolution depending on their composition and their mass and so on.
Well, with a computer
And the
sim,
universe itself has is like a person, if you like. It has a birth, a youth, an evolution, and so on. And nowadays, our universe is about 14 billion years old. So when we do these simulations, we follow the evolution of the universe from its birth until today.
well, with the information that we have now and using a computer simulation model to recreate the exact one that we're in, has anything ever come close? Because I start picturing it like a probability thing where you're getting, oh, your number is going to be 7, but this thing goes up to 1,000, or let's say infinite, and it's just keeps popping out numbers and you keep refreshing it until it hits that 7, which hasn't. I mean, that only gets better. You're able to limit it, or I guess more define it with the more information that you discover. And right now, as crazy as it sounds, it's the golden age of discovery for the Milky Way. Mostly because of all the vast telescopes that have been created. I think there's 2 primary ones from like the 90s or something like that. You're surprised I know all this, mostly because I was Googling before our chat. But when you really kind of take hold of what information, what things, you can really start to get the real kind of close to what I would say a replica of exactly how this universe was created, which makes us really understand our origins in a sense as well, too, before even life was really created, but when the planet that we live on was created. I'm just curious too, what are the challenges and also what are the, I guess, progress you've really seen in trying to really narrow down or make that computer simulation really recreate this vast universe that we're in?
Yeah, that's a good questions. Indeed, I think it really. So we know very well the physical laws. We know the force of gravity, and we also understand how stars evolve and so on. So we also know the down to the bottom of the physical laws. We understand the electromagnetic forces very well, and so on. So that's not the issue, but there is an issue with initial conditions, which are very poorly constrained, especially in the when we talk about galaxies. So, for example, with the Milky Way itself, we know how to create a generic galaxy that kind of looks like the Milky Way in a computer, but we don't actually know what were the initial conditions. And the end result actually matters very strongly on the initial conditions. What were the initial perturbations that you put at the beginning in terms of matter density fluctuations? And what is the history of accretion history of the galaxy? So you mentioned, for example, that we're head on to Andromeda, which is our sister galaxy. This kind of collisions happened in the past as well, not as big as the future merger that we're going to have with Andromeda. But we had, for example, one of the satellites you mentioned, Gaia, discovered a big merger that happened about 10 billion years ago between the Milky Way and a galaxy which is a bit smaller, the size of the Large Magellanic Cloud, and that made a big impact. Now, without this telescope, we won't actually know that the impact happened and the time and the mass of this galaxy that crashed into us. And what we actually observe today is just the debris left from that major collision. So these observations actually help us when we do theoretical modeling to kind of tweak our models to actually find within the myriad of possibilities of galaxy mergers and galaxy evolutions, the one that actually looks like the Milky Way.
So what's the computer simulation running off of? Are you guys listening to the theories out there that this thing just miraculously just exploded, or this something happened and all this thing started kind of setting the basis or the base layer of when these planets started to form? Or are you looking at maybe another collision event, something that was way, way before? Because I'm looking at this computer simulation as the, I guess, the key to the puzzle in a sense, because if this thing randomly spits out the exact, I guess, computational whatever program of what this universe is, then you kind of look at it like, well, if it did it once, then let's keep sticking with that algorithm, see if it does it again. And if it's able to replicate it on a certain amount of times, you can not only narrow it down, but you can also figure out what happened with the technology that we don't have to look back further? Because it seems like it's 1,000 times harder to try and go back in time to figure out what that was there with actual technology in this time period. You would have to develop a time machine.
Yeah, so good question. What we actually do is because we don't actually know the initial conditions, our approach in our group is, for example, to simulate a lot of galaxies in the hope that they would actually look like the Milky Way later on. As I said, we actually know the physics very well, and we try different initial conditions, just rolling the dice with different initial conditions and see whether sometimes you get a spiral galaxy that looks more like ours. Sometimes the crash is between galaxies is so strong that you destroy the spiral disk and turn it into a blob of matter that looks more like a elliptical galaxy. So, but we do have nowadays very powerful supercomputers, so we can afford to run dozens of simulations of different galaxies with very high resolution. And if you like to do at less resolution, we can have thousands of galaxies simulated on a computer. So we have lots of toy models. And then we sift through the data. Once we get these observations, we sift through the numerical data and we find some galaxies that kind of look like what the data, observational data are telling us. And then we go back and reconstruct this specific merger history on a computer with with better numerical resolution. Yeah, so that's what we're trying to do.
Have you made any jumps forward in, like, say, like the past 5 years? Is there I guess, anything that's been some breakthrough evidence? I mean, have we gotten super close to getting, I guess, the right simulation or the right, I guess, number when it
Yeah.
comes? Okay.
Yeah, so it's funny enough, I've been in this field for long enough. When I actually started my PhD, the computer simulations were very poor. We weren't able to form even a generic disk galaxy on a computer because the physics was a bit off. And in the past, 10 years or so, the simulations become very sophisticated, so we can actually get very realistic galaxies. Now we're really talking about fine-tuning the simulations to have an exact replica of a galaxy that looks like the Milky Way or like Andromeda or things like that, in the hope that we can actually understand better how our own galaxy came about. Now, obviously, we are a bit, we like to put ourselves in the center of the universe, and that's actually not a good thing if you're an astronomer to kind of think of we are having a special place in the universe. And it kind of goes the same with galaxies. We should avoid trying to be too galactocentric, kind of believe that our own galaxy is a special galaxy in the universe. So this kind of simulating lots and lots of galaxies also help us understand whether whether our galaxy is unique or has something special compared with other galaxies, or on the contrary, something like more run-of-the-mill galaxy. And yeah, so I think over the time, the simulations became very, very sophisticated. And now we're getting at a stage where we can really do very good comparisons with observational data. And this is really prompted by the huge amount of observational data that we gathered in the past, I would say 7 or 8 years. There's been a huge revolution in this field thanks to a satellite called Gaia, which has been launched in December 2013. And Gaia is still up there just measuring positions and dynamics of stars in our galaxy. And this is for the first time we've actually been able to have a full map of the galaxy, believe it or not. It was before Gaia the observational data was very limited. And now we have about 1 billion stars mapped very precisely with Gaia. There's still not all the stars in a galaxy. We have, I think, many more, like 100 billion stars in the galaxies. It's just a small portion that we've been able to map observationally, but is the first big step, a big jump in our understanding of the galaxy. And this is how the merger with this dwarf galaxy 10 billion years ago was observed thanks to Gaia. And of course, Gaia also gave us lots of other major discoveries about the Milky Way. For example, we now know there is a giant wave of gas going up and down through the disk of the Milky Way, like this giant snake. And the sun is actually very, very close to this giant wave of gas. And it actually, calculations have shown that the gas actually passed through this giant snake a few 100 million years ago. And it's a very interesting question because this wave of gas, these gas clouds are enriched in some elements, for example, iron and so on, that could have polluted our Earth a few 100 million years ago. So it also ties into the questions of where we're coming from and whether our sun is a star that has been deposited through a merger with another galaxy. So in this case, we've been aliens produced by our planets and sun have probably been produced in a different galaxy and they just deposited in the Milky Way. Also, the elements that make the composition of the Earth today could have been polluted by the sun and the solar system just traveling through space and just acquiring elements for life from different parts of the galaxy.
Well, how much weight do you put in the fact that maybe that this combination or this mixture that this halo or whatever you want to say is forming in our galaxy could possibly spread materials or some type of elements to other planets and actually drastically affect their change? A lot of people bring up this theory that an asteroid hit Mars and some space particles floated off into Earth's atmosphere and we evolved from those space particles. That's why people like to say that we're from Mars in a sense. Now, I mean, I don't think it's that ridiculous. It might be, but when you really start understanding the amount of cosmic events that happen out there, you can't really chalk it out. Like you have to kind of keep it still lodged up in there. I'm just curious to where where are you getting your resources, or are you asking other astronomers? Are you just getting it from the telescope in general? Because I would think that everybody who has at least a hand in the astronomy section or just looking up into space in general probably has a good input on these types of things as well too. And then my second question would be, are we looking for anomalies as well too? Or is this type of technology or the type of field that you're involved in, is the simulation for the computer program, is it being used to look at our origins, or is it starting to be more funneled into looking at what the future is going to be? Because especially with AI, it seems like people are using AI in a large, I guess, gap to fill with being able to predict the future, mostly with just probable outcomes of what will this route take or what will this route take. And I mean, yeah, that's a worry too. I mean, that center of that Milky Way galaxy is a supermassive black holes. So, I mean, we're now starting to learn about those, dark matter as well too. I mean, these are all really like it can really give you a panic attack. Like I need my inhaler. I gotta go, like take a quick breath in just to catch it. But it's interesting because especially because I'm just a common person just looking at articles and trying to read up as much as possible, and you don't really realize how expansive the science is, where you start realizing, especially with AI, the capabilities of it are immense. And I think when we look at studying our origins is a good aspect, but it's also something that's like it'll be random when we possibly get the answer, unless something drops right in our lap that gives us a very crucial piece to that puzzle to be able to put it together. It's 1,000 times easier to look towards the future of what's going to happen because we can predict with the deterioration of a lot of events seems to be the direction that we've been using AI to try and fix that deteriorating aspects to it. I mean, it's a lot. I gave you a lot. I'm sorry, I didn't mean to rant there, but it's
No,
interesting.
it's all good questions. Where do we get our data? There's a lot of data that comes from this. So there's different strands of data we can use for our simulations, not well to compare our simulations with observations. So there's, for example, this Gaia telescope measures kinematics of stars. So we look at how the positions of the stars in the galaxy, just a clean map of the Milky Way, where the position, where each star in the Milky Way is, and also the positions, the velocities, how fast the stars move in space. So there's a lot of information encoded just in the positions and in the way, the speeds of the stars, because this is for example, some tracers of past mergers of the galaxy would be encoded in the dynamics of the stars, how fast they move or the direction they move. If we see a bunch of stars that really stray in a totally different direction than we expect, they're probably some alien star that came from a different galaxy that just bumped into ours. So the kinematics and the positions are very important. There's other type of data we're using, which involve spectroscopy. So we put a spectrograph on a telescope and we get some absorption lines. We look at the composition of different elements in stars, in the atmospheres of stars. So for example, our sun has hydrogen and helium, but also has a little bit of iron and some other chemical elements. And our Earth has a lot of chemical elements that come from elsewhere. They haven't been produced here on Earth, or not even in the sun. So for example, the iron in our blood or the calcium in our bones and so on have been produced in some stars other than the sun. They've been exploding a long time ago. So the type of stars called supernova explosion. So this supernova explosion, you have to have a very massive star, more massive than the sun, to explode as a supernova and just spill out in the universe this chemical elements that later on rain onto different planets and so on, and are conducive to life. So having also spectroscopy, so analysis of different absorption lines of stars, it's also useful because we can extract a lot of information just from a spectrum of a star atmosphere. How much iron is in it, how much calcium, and so on. And then, yes, with computer simulations, we can actually model the dynamics of all these particles. So the galaxy has a few 100 billion stars. So each star will have its own dynamics and its own evolution. So you can see right there, this becomes unmanageable. Even if you know very well the physical laws, you can't actually, it's not tractable to just modeling pen and paper. So you actually have to put all this into computers, and the computer will crank up all the data for you and will model in the future, model the future modeling of the whole galaxy as a system of stars. And yes, the AI is very useful. The machine learning, in principle, we are at the stage of applying machine learning techniques to galaxy modeling. And obviously in the future, AI will actually help us develop possibly new models of galaxy formation. But the machine learning techniques are very useful because, again, they could sift through the data and find weird patterns. Some of this debris from past collisions with other galaxies is so mixed up in the galaxy that it's no hope for us to find it. So then a machine can learn how to extract this information from the huge amount of data that is presented from the telescopes. But also through these computer simulations produce lots and lots of data. So we can produce terabytes of data with galaxy images and information about positions of stars and their chemistry. And again, a machine could learn how to go through all the simulations and extract the useful information. What is the crucial thing that we want to know about the Milky Way? So this is what the machine learning is. The machine learning is very good, for example, at detecting any surface brightness variations in an image, that very faint features that our eyes may not be able to pick them up from an image, but the machine learning technique would actually pick them up.
How much weight is being put into the fact that maybe dark matter might play an essential role in the creation of the Milky Way galaxy?
Yes, we should thank dark matter for being here, because without dark matter, galaxies could not form. That's at least what we think. Most of the matter in our Milky Way is actually dark matter. So, and this goes the same for all the other galaxies, that they're very dark matter dominated. And in fact, if you take out dark matter altogether from computer simulations, you can't actually form large galaxies like ours, and you can't actually evolve the universe very well. So we actually know there should be a lot of dark matter in the universe. Now, what is dark matter? It's a different question. We actually don't know what dark matter is.
Have you been able to at least pull out some, I guess, data from it when it comes to maybe what a frequency that dark matter is on? Because, like, if I was going to ask you to put all your chips in, all your gambling chips in the pot, on what you think created the Milky Way galaxy, because when we start talking about it and I kind of start thinking about it, I start looking at, like, if there is dark matter that I guess composites most of the Milky Way galaxy, what happens if one of those had an elemental shift to it, or had something about that its normal rate or whatever, if we don't know what its normal rate is? But what happens if one of those, or if it's, you said the Milky Way galaxy is formed of dark matter. Imagine if just one of those, just like an atom, if you change a neutron or whatever you want and you change it by one number, it kind of throws everything a little bit differently. I start going, what happens if one of this dark matter pieces decided to change a little bit or go to a different frequency or something like that? Would you have some type of combustion? Would you have some type of response that would create something like the Milky Way galaxy? Because if you're looking at the Milky Way galaxy, besides analyzing how it is, how beautiful it looks like an implosion. It looks like something exploded upon itself, and then you're seeing the remnants of that. Now, if that's what we're understanding what this is, and it's be able to create this much and it's able to form the way it does with vast other variations or anomalies of patterns, whatever you want to say, happening all at once, you start going, what created that initial explosion? Because if there was just nothing and then there was something, something had to happen that we can't see at a microscopic level that we haven't been able to read yet, which means that if it's something that we can't perceive with our eyes, if it's something that maybe technology can pick up, but we don't know the exact principle of, it seems like that would be like an internal change, which might be something we can't really analyze yet.
Yeah. So, but your question about changing dark matter, if I understand correctly, I think yes, there's a very good question. But actually, because we don't know what dark matter is, and we're talking here about candidates for dark matter particles. If dark matter would be a particle, it would be very good to know what mass that particle is and what are the properties. And at the moment, there's a wild guess of what this mass of a dark matter particle would be. For the longest time, we thought the dark matter would be from a class of particles called WIMPs, which stands for weakly interactive massive particles. So unlike the name, a WIMP is actually a very massive particle. And for that reason, that it's fairly cold, doesn't have a lot of interaction, doesn't move very fast, and also being dark matter, and it doesn't interact with normal matter at all through electromagnetic forces. So for this reason, you can't observe it with our telescopes. It doesn't emit light, and it doesn't emit light and doesn't absorb light. Now, because for the longest time we actually looked for this dark matter, we couldn't find it. Now we also thinking about changing a bit the properties of this potential dark matter candidates, just to look around what in the zoo of potential dark matter candidates, which one would actually fit the data from the Milky Way better. And as you say, we can actually change a bit. We can make it a bit hotter or warmer rather than cold, and it means that the particle will be a bit lighter and will move faster if it's hotter. And that would actually, although it still doesn't interact with the normal matter that makes you and me through electromagnetic forces, will still interact through gravity. But because it has a different speed, it would actually and a different mass would actually change the properties of the Milky Way over long periods of time. So yes, you would actually, for example, if you have warm dark matter, then they will have less collisions because the bigger you will form less galaxies in general in a universe. It will be more smeared out. So our Milky Way would have fewer collisions. It will have a more quiescent formation history than we think it has. So we can actually put all this scenarios in cosmological simulations, change a bit the nature of dark matter, and see what happens. So we can do this in parallel with changing the initial conditions. We can change the initial conditions, but we can also change in the same time the nature of dark matter and see what kind of scenario is more plausible.
Because I start examining it like a magnet. When you get the north and south ends of the magnet, if you have the two of the same that try and touch each other, they try and push each other away. So I go, if one of these dark matters, if you have let's do like a fly swatter amount, like there's like 50 of them all in one area and they're all lined up perfectly. One goes out of line and it happens to be in the middle. You're going to have this quick adverse polarization that's going to push everything away. And this is where you get that. Because it looks like if you took a ball of dough and you slammed it on the concrete, that's what the Milky Way galaxy looks like. It's this thing that looks like a frisbee in a sense, but with a centerpiece to it. So I'm like, that would be something that would implode on itself, but I'm wondering if that could possibly be what it is. Now, when I asked about putting all your chips in to what you think the origin would be, because I'm about to take us in a whole different direction in a second, but what do you think the origin was? Do you think it was something like that? Do you think, I mean, there's no air in space, right? I'm just going to toss out random ideas, but did someone blow on a particle of dark matter and see what happens with that? Was there an oxygen added that could have been that change? If it was something that changed about this form of dark matter, I mean, our research into dark matter, if I'm not wrong, is pretty recent compared to how long we've really been studying the galaxies in a sense. Like no one really even knew it existed at a point.
Yeah. Um, I think you have a very you have a view of a violent formation history of the Milky Way, and that's possible. But I see it. You mentioned dough. I see it more like a slow cooking. You form, or like baking a cake, and just put these ingredients. Your dough would be your dark matter, and then just put toppings, which are the gas and the stars, and you can actually slow cook a galaxy over a long time without having this big merger events. Now, what dark matter does is it's first of all, it helps your galaxy grow because it feels the force of gravity. So because the dark matter is already there, it just helps attract more matter into it. So that basically could attract more dark matter, but it could also attract more gas. And your gas clouds are this fuel for star formation. So the dark matter is beneficial for having in there because it makes your galaxy, your cake, grow bigger with time. It can also be destructive because all these mergers with other galaxies, they also are very massive because they come with their own dark matter. So you have big collisions between galaxies, and that could be destructive to a galaxy. So it's a destructive event, but it also, the galaxy is very resilient when you smash these things into a galaxy because there's gas and the gas can form stars. You can actually recreate the spiral disk of a galaxy in a very short time. So this is also a surprise we found out with the Maker simulations. It was thought that if you just bang two galaxies into each other, you just destroy them altogether. And but it's not true in a sense. What we see in the simulations is as long as you have some gas cloud, the gas always wants to form stars, and you would form this galaxy in the end.
Well, so
if how do I bet? How much bet do I put? Correctly on dark matter candidates? Not much, because we've been looking for dark matter for a long time. So I think the first person to actually hypothesize about dark matter was Franz Zwicky, which was in the 1930s. So more than 70 years ago, or 90 years ago. And then I think it was a bit later than that. But anyway, for 70 years, we actually knew about this dark matter, not in our galaxy, but for example, in bigger collection of galaxies called clusters of galaxies. And then in the 1970s, there were some very interesting results from the group of Vera Rubin and some other astronomers who looked at how fast other galaxies rotate. And it turns out that they were rotating much faster than they were thought they should be. And this difference in the rotation speed was explained through the presence of dark matter. So we always had some hint there is dark matter in galaxies. We've never been able actually, even today, to actually pin down what is the dark matter particle, to actually detect it through a telescope or through an experiment or anything. So it's not for the lack of trying. We try to, at CERN, people have smashed particles onto each other in the hope that they would create this dark matter particle. There've been experiments in space. There've been telescopes on the ground to measure, for example, very energetic gamma rays that might come up from annihilation of two dark matter particles. So lots and lots of experiments, but so far there's no clear detection of dark matter, either directly or indirectly. Just this. We see it through how it affects stars and gas, but we cannot detect it directly.
Yeah. Well, has anybody ever thought about dark matter being here before anything else was here? Like what came before? Maybe it was just here. Like space, if you really ask people what space looks like, besides the stars and all that, it's black nothingness. It's just an endless kind of void that goes on and expands upon itself into endless more nothingness. So I wonder, has dark matter just always been there? It's just been a part of this thing, and these elements or these things that get added in, this thing that you say grows and helps grow a galaxy. I mean, that's not what it was intended to do, but that's what it's doing. It's because it's always been here. It's not like it was added in from another galaxy, but that makes me curious if there are other galaxies out there. How old are the other galaxies? Have we been able to predate those? And are we the youngest one? Because then I start thinking, if we are the youngest one, then wouldn't we just be all the runoff of all the other galaxies and all those elements that get added in?
Yeah, that's a good question.
I'm an outside thinker.
Yes, because this formation of a galaxy is an organic process, so you can't actually put a number on the age of a galaxy, because there's some older bits and some younger bits in the galaxy. The things that have been dumped from more recent mergers, they're young. But we've been able to actually measure very old stars in the galaxy. So the oldest stars that we detected, they're about 10 or 12 billion years old. Now, to put in the perspective, the whole age of the universe is about 13.7 billion years old. So the first stars that form in the Milky Way were formed quite recently after the Big Bang, so quite soon after. So in a sense, our galaxy has been around for a while, but not in the shape that we see today. It might have been a very small galaxy, what we call like a proto-galaxy, like just like the incipient part of the galaxy. And on top of this, you got different bits accreted much later, so the galaxy grew up in size. Yes, if dark matter was when was dark matter formed? That's a question that actually, in order to answer it, we need to know the properties of the dark matter particle. So if the dark matter, as I said before, is a particle which is very massive, like a WIMP, that means it has been formed very early on, even before the normal matter that makes you and me, like the protons and electrons. Because it's more massive, you need more energy to produce it. You know from Einstein's equation that relates energy with mass. So it was formed a bit earlier, but still it has to form after the Big Bang. So it's still a finite age. Yes, it might have formed earlier, and as I said, is lots of dark matter. Is much more dark matter in the universe than normal matter. I think if you sum up normal matter, like protons and neutrons and electrons and dark matter makes about 85% of it. So it's this way, for any proton, you have many more dark matter particles. In fact, right now, when you and me are talking, there's like gazillions of dark matter particles going through you and me, and we actually don't feel them because they don't interact with us at all.
I kind of like a better example, or for layman's terms, for anybody out there listening, at least the way I'm understanding it, is that it's kind of like when you set up a garden, the fence that keeps you inside the garden to build up your garden, that's the dark matter particles. And that gives us the limit to be like, okay, we can build up in this area. Because the way that a galaxy, at least the way you were describing it and the way I understood it, was a galaxy is a lot like a city growing at first. You have one house, and then eventually you have a whole landscape of houses all beside each other with an electric grid and all these add-ons. The more time, the more it can grow in that sense as well too. That just makes me want to examine, which I know we probably can't without computer to be able to do it for us, but take it to use a computer program, take it back to the very, very, very beginning before you could predate these stars that are 12 million or 12 billion years old. Because I would think if you're creating something for the first time, like not analyzing it from a God perspective, because I'm not religious at all, but I'm saying if it's something's going to be created like out of nothing, there's nothing there for it to start on. So it's going from nothing. It's going to be probably huge, but it's going to have no funny attachments to it, no add-ons, none of these bonus features. And then after a while, it just becomes more defined. It becomes more this, which starts to make you think, does this universe have a consciousness in a sense? Because you look at how sophisticated everything is, and you're like, this is like something's thinking of this, or these are just random events that are somehow happening, and it's somehow appealing to us to where we make it think this way. I mean, it's interesting stuff because it makes you really examine, makes you want to walk outside and grab a telescope and look up. Because you really start examining things, especially the amount of things that you can't see and that you don't know information wise that we just don't have yet, what these possibilities could be. But man, when I look at dark matter and how we're researching into it, even saying that these things don't really interact with us and they're constantly around us, I mean, what we can't react to it, sure, but what can react to it? You know what I mean? I start going like, maybe we can test a bunch of things like this doesn't work or this doesn't work. We can change it, make it hotter, we can make it colder. That's good for like humans to be able to see that. But from like a universal scale, I start wondering if there is this void of space that is constantly expanding, what are the primal things that inherited or live upon that before we even came to be or before any stars became to be? If you start wondering about stars that burn out and we look at a star, that thing could be burned out for like a couple million years. We don't know. The light's still traveling towards us. Imagine if that light is a key aspect to growth, like seedings. It's something that gets trapped in, or maybe some pieces of it, some of that energizes one of these atoms of dark matter. I don't know. I'm speculating now. I'm trying to look at like the galaxy in my head. I really am. And it's so hard because I can see the Milky Way. But then when I try and expand past that, my knowledge doesn't really go out past our Milky Way. It kind of stays in the basis of that. So I'm trying to picture the grand map. And I know we're only covering a small, small, small portion of what is still out there.
Sure. No, I think from what you describe, you actually describe how matter comes out of energy. And I think when you ask what was originally out there, well, it was energy. Because when the universe there was a big bang, there was a lot of energy there at the big bang. The temperature was immense. And because the energy was so high and temperature was so high, there was no way you could have matter in that hot environment. So it was just energy. And from that, as the universe expands and cools, then you can form protons, you can form electrons, you can form more bigger elements that can synthesize elements that go on into atoms and so on. So you can form hydrogen and helium. Dark matter also was formed from energy. So at some point, if the mass was very big, at some, you have E equals mc squared. So at some point, it was just an energy. And when the universe expanded and cooled off, that energy was transformed into a particle. So yes, dark matter preceded us. Now, yes, it's good to have this ground view of things. As I said, we could be kind of closing ourselves in and just seeing the whole universe through the perspective of one galaxy, which may not be that special at all. The Milky Way could be just your, a regular galaxy among the gazillion.
It could just be the runoff of all the others. That's what you got to think of.
Yes. So yeah, the universe is immense. But the thing, we physicists, we also have a principle which has never been contradicted, which is basically an assumption that the universe is the same everywhere. So our patch of the universe, the physics is the same as another patch of the universe. So we call it the anyway. So it's a principle, and so far we haven't been contradicted that the universe it's pretty much the same. So if you understand dark matter and formation of dark matter and gas and stars on a local patch of the universe, that should be the same on any other patch of the universe.
But do the galaxies, okay, hold on. So you're saying just like the same information you could get out of this universe could be transferable to another universe as well, too?
No, that's a different question. Yes,
Okay.
because our universe is, well, if you believe there's a theory called the multiverse, and there's actually a prediction from the inflationary theory as well, that you might have a multitude or maybe an infinite number of universes out there, and our universe could be one of them. And then again, it's just rolling the dice. What are the initial conditions of our universe? And then our universe, thankfully, is very good for life because we're here, and we know that So there's some very puzzling elements to our universe. It's if you look at the constants of nature, and strength of the force of gravity, or that the different elements that go into different concepts that go into electromagnetic force and so on. They're very fine-tuned so that the galaxies won't fly apart. You can form a galaxy over a long enough time. You also need a long time to form galaxies so that you can enrich them in different elements, like, for example, iron. You have to let enough time for the supernovae to blow up and spill the metals into the cosmos, and then that elements go rain onto different solar systems. So you need a very delicate balance between the formation and death of stars and so on. And again, with dark matter, if there will be much more dark matter than it is, then we'll have a bigger problem for the formation of galaxies. So everything seems to be a bit fine-tuned for galaxies to exist, and then for life to exist as well. Now, that may not be true for other universes, because they might be born with different initial conditions, with slightly different composition of dark matter and baryons, and they might be short-lived. For example, if it has a lot of dark matter, that the universe will expand, but then will collapse on itself, and just you go from a big bang to a big crunch.
Now, I want to take it in the direction I said, where I'm going to go way off track. When it comes to the future capabilities of using this technology as well, too, to predict possible events, I'm wondering, is that being used, if it was being kind of pushed in that direction, which I would only, if I can think of it, I'm sure other scientists have thought of it easily, but I'm curious to where they could use it to try and fix core issues that like our issues on our planet, like global warming, for instance. If you're able to see an ice planet or some type of ice giant that's close by in our solar system, is there a computational model or some type of program or programmability, I would say, to predict the possibility of being able to warp that planet or warp whatever, or just add something into our atmosphere to be able to cool the planet? Like, I know they're talking about, like, what's that term? Not geothermal, it's
Geoengineering.
yeah, but it's like terraforming, but this would be more of a universal thing, where you start looking at, like, ways to be able to manipulate or add, like, just like how our universe is created. If our universe was created with a bunch of particles coming together and all these types of things, and over a long extended period of time, this formation, then try and do that in a short amount of time, but at a smaller scale, to not affect the universe, but affect one planet. You start looking at ways. I know there were theories out
Yeah,
there of,
no,
okay, so
yes,
I'm not
of
wrong.
course. I mean, this being computer simulations, you could just keep the simulation running, so you could actually predict what happens with the galaxy in the future. There's no way, and there's nothing that stops that. You put the physical laws in the simulation, and you know the position of all the stars today, so you can just compute what will happen in the future. And people have done this. Of course, depends on what questions you ask, on what scales. If you're interested in the collision of galaxies, we know, for example, what will happen in about 4 billion years from now, a long time, when our galaxy would merge with Andromeda. Now, there's no reason to panic. Obviously, it would not be there, but even so, in these galaxy collisions, they have been no impact on the scale of solar system or on individual stars. So the space between different two stars in a galaxy is big enough. So there would be a merging, so the two galaxies will become one, but there would not be that would not translate into star and star collisions or any disruptions of solar systems. So people have run the simulations to see just what will happen in the future. And it's actually very nice to see that the sky will be completely different. Right now, we look at the sky, see the Milky Way, this band of stars, but 4 billion years from now, the sky will look like a mess, because you have this mess of this huge debris from Andromeda. First, you'll see Andromeda closing in to us, see this big thing on the sky, Andromeda growing bigger and bigger. And then, of course, when it collapses onto the Milky Way, the sky will be totally different. Now, on that scale, obviously, the solar system will be completely changed, because the sun itself has a much smaller lifetime. The sun itself will evolve into a giant. So then a red giant, and the atmosphere of the sun would just engulf the Earth. So that the life on Earth at that time would be will not be able to exist, at least connected to Earth. What happens, of course, these simulations, you can run them at much smaller scale. So the scale is, you don't need to simulate the whole universe to find out what's happening in the solar system. So you can just simulate just the solar system. And yes, it's the same laws of gravity, and you put, all the positions of the planets and the moons and asteroids, and then you put that into computer simulations and you predict what happens in the future. And I think that's very useful, of course, because we want to know where all the asteroids are. And for most of the asteroids are already known. But for example, Gaia has, as I mentioned earlier, there's the satellite that's looking at the Milky Way, but is also observing these transients, these things that just cross the field of view, and they're actually objects in the solar system, and has discovered a few new ones that we never knew before they existed. So it's good to actually have a updated map of all the objects in the solar system. And yes, I think all these models are they're always evolving as soon as we have more information about the objects in the solar system.
How do you take into the fact or add into the equation anomalies like a Moa? Nobody was expecting a Moa, or at least from what I've heard, nobody was expecting something like that. So I look at, if you're analyzing our universe and you're adding in anomalies, I mean, how do you add in something that has never happened before that is randomly drifted
Yes,
in?
that's a good question. Well, I don't know what a Moa was, but to just give you an example, that an anomaly in the Milky Way. Gaia has discovered some stars that move very fast. So maybe that would be a good analogy with Oumuamua. So, this object was just an object that came from nowhere, came very close to us, and then disappeared, right? And this one object was not necessarily predicted, and also the shape and so on. But on a much bigger scale, we also have an anomaly with the speed of some stars in the Milky Way, which we call them they have a hyper velocity. So that these velocities are much higher than we were expecting. And that shows that they're not necessarily gravitationally bound to the whole galaxy. So they're just the stars that come from nowhere, come into the galaxy, and then they might escape. They may not stay around for too long. And again, they could be related to the galaxy collisions. But yeah, so for example, when we have these anomalies from observational data, we go back to simulations, and first we try to find out whether our simulations ever have any populations of stars or any objects that have these anomalies. And if we don't, then we just go back to the drawing board, and then we just say, okay, what do we need to do in the modeling that we do? Maybe we're not modeling star formation very well, or the dynamics of the objects, or maybe the history of galaxy is not very well constrained. So these kind of anomalies are very useful. And actually, these are the things that you don't actually understand are most useful for advancing the field, and the things that you understand. We're not looking for just matching our simulations with observations, say everything is fine. We're just looking for things that kind of jar with our understanding of galaxy formation.
Have you ever had anything that threw a monkey wrench into all your progress and made you want to restart back from the beginning? Like, I feel like the understanding of dark matter is only going to change the whole sketchboard. Like, our deeper understanding of it, you could come across something that would be like, oh shit, this was like the thing that led to all this. So we can just, everything we've done from here can just be trashed. We got to go back to the start, but add this in there and we're going to see a whole different timeline.
Yeah. Yes, we have lots of problems. And I think, our galaxy, so for example, the Milky Way has all kinds of little galaxies swarming around it. We call them dwarf galaxies because they're very tiny. But because they're very tiny, they kind of break down our understanding of our theoretical understanding of how galaxies form. They have lots of dark matter and very little gas and stars. So we don't actually understand how you can form a galaxy on such a small scale and what are the physical processes. So these kind of objects kind of break down our modeling a lot. Yes, there's lots of physical processes that may go wrong. For example, the supernova, then when they blow up, they have some winds. and maybe the winds don't have the right speed, or maybe the pollution of elements inside the dwarf galaxy is not the right way we think it is, and so on. Yeah, so lots of problems, and this is actually what I'm working right now, trying to figure out where our models break and why do they break, and so on. And unfortunately, well, let's say maybe fortunately because it makes you think, but unfortunately, these problems we have with modeling the gas and stars are very tied in with the models, with the problems we have for modeling dark matter, because there's two big unknowns and they could just overlap. We have two unknowns on top of each other. And when you don't actually match the observations, you're not clear. It's not clear whether it's because your model of dark matter is wrong or because you don't actually model the things you should know how to model, like the gas and stars.
I bet it's got to be extremely difficult. You probably have to have a really open mind. Like you can't really have any closed opinions on anything. And that's like one of the most difficult parts about science is that a lot of scientists, I'm not saying you, I'm just saying a lot of scientists or is really trying to get your name or name on something like discovering a new star, you really get to name it, discovering something new, you get to name it. So if you have a probable theory or an idea of where this went and someone goes to throw a monkey wrench in it, that's like the hardest thing. Like, you have researchers that'll smear someone's profile or anything, all because they want their 40 years of work to matter, even though it could just be completely thrown out, which is difficult. I understand it. I mean, I'm not saying I'm above those people at all. I'm just saying it's a complicated subject when you really look into science because it's so hard to leave ego at the door, and really put that revolutionary step forward of thinking of the human race or the human species. A lot about it's like what's going to make sure that it all pays off for me, all my work pays off, So it's a very, very open field.
Of course, obviously, like any other fields, science, you need to navigate these psychological um, uh, issues. And yes, there's a lot of egos in science, but I think overall, I think the scientists want to actually know the truth. And it's funny because science, as you look the scientific field, if you look at it, it's a self-regulated field. There's no one apart. Obviously, we all hired by universities and so on, but no, is no one telling you what you should study or what you should think, and you kind of develop this your own. Um, this actually that's what I like in science because it leads to creativity and you actually think of problems on your own. And of course, you can put some problems out there and they get completely smashed. Everyone would not buy your idea at all, or sometimes maybe out of these 10 ideas you put out there, maybe one works and then it's very interesting. The thing is that when I've been in the field for a long time and all the theoretical models have flaws, and that's not a big deal. We kind of get used to it. We're trying to kind of minimize these flaws and trying to fine tune our models to actually compare with the observations better.
Well, we know, I mean, you're doing pretty good for knowing that there's two giant unknowns basically that kind of you have to work around. It's kind of like me limiting you to one area and you're like, okay, well, this is all the data I got, but there's two giant pieces that would really help us out. But I guess it's like trying to eat a salad without a fork and a knife. Like you're going like, I can still eat it, but I mean, it would help if I had the utensils.
Yes, and it's true. I think the field tends to be very structured, and so there's scientists who actually are interested just in dark matter, and some scientists are interested just in normal matter. And then it's good to kind of be in the middle to see, try to understand, because there's the scientists who work mainly on dark matter, they're trying to ignore the uncertainties in the normal matter and vice versa. So I think that's probably not a very productive way of advancing science. To actually have put all the uncertainties together and to analyze, even though it makes the modeling much more complicated, that's probably the only way to kind of advance and the more general model of galaxy formation, which includes both dark matter and normal matter.
From what I've heard from so many geologists, the best explanation I've ever heard is that it's about the younger driest impact hypothesis. They go for the longest time, astronomers looked at the skies and geologists looked at the ground and they never talked. And I was like, yeah, that makes a lot of sense. They're both kind of working on their own different paths in a sense, but maybe they have the both crucial information that could let insight into both their discoveries. It's an interesting little saying, but it's been a pleasure chatting with you. Seriously, my mind's still thinking about like galaxies and dark matters and all this. It's probably going to be on my mind for the rest of the day, but it's a fascinating subject. I'm really happy that you decided to come on my show and be able to educate me a little bit more about it. Is there a place where people can find you? Do you have any links?
Yes, they could check my university webpage, and there's a webpage just dedicated to this cosmological simulations that we built. They're called ARTEMIS. So they go to astro.ljmu.ac.uk/Artemis. And yeah,
Twitter?
my personal website also has some links.
You got a Twitter? I know you got a Twitter.
Yes, I have a Twitter. I'm not much of a Twitter at the moment, but yes,
I'll link it anyway.
as well.
I'll link it in there. But it's been a pleasure chatting with you, and thanks for listening to this episode of Out of the Blank Podcast.